In section 3.4, we're going to talk about growth and decay rates. So we talked a bit about growth and decay factors in the last section, and we just a tiny bit mentioned what a decay or growth rate, it was a growth rate was going to look like. We're going to fix that up and talk a lot more about it in this section. So we're going to talk about determining the annual percentage growth or decay rate of an exponential function represented by a table or an equation. And we're going to graph exponential functions having the equation a times 1 plus r to the x. And some other varieties as well. Okay, so talking in this first situation, according to the U.S. Census Bureau in 2016, the population of Belleville was 141,400, and that was in our 2016 year. Assuming the population increases at a constant percentage rate of 1.3%, determine the population in the next year in thousands in 2017. So since we're going to use the units in thousands right here, let's just go ahead and call this 141.4 thousand. So that puts thousands as the units, or thousand as the units. Okay. All right. So we need to figure out if I increase by 1.3%, where does that put us? I'm going to refocus real quick. Hope that's better. All right. So I'm starting off at 141.4 thousand times 1% is 0.1, so 0.13. And that means I'm going to increase by an additional 1.8382 thousand. So if I add that to the 141.4 thousand, that means that in 2017, we have our 141.4 thousand times the 0.013 plus the 141.4 thousand. It puts us at 143.2382 thousand. Now we're going to determine the population of Belleville in 2018. So we're going to take this number and we're going to multiply it again by 0.013, and we're going to increase by a 1.862 thousand on top of the 143.2382 thousand. So when I write this down, I'm going to note that I'm taking the 143.238 times 0.013 plus the 143.238 equals 145.1, and then a bunch of zeros, 0.1002. So let's just call it 0.1 thousand. Okay, so now we want to compute the ratios. We're going to do the ratios of 2017 to 2016 first, the ratio of those two. So we're going to have our 143.2382 divided by our 141.4. Sorry, my decimals is in the way, but I want to keep it up here because I need to use it. 143.2382 divided by 141.4. I mistyped that number on top. There we go. There we go. Okay, so this ratio comes out as 1.013. We're going to do the same thing for the next two when we want to do the ratio of 2018 to 2017. We're going to do the ratio of these two values. So I'm going to move decimals off to the side just a little bit more here. We're going to need to do our 145.1 over our 143.238.2. And let's see what that gives us here. Okay, so it gives me 1.0129, which would round, but I'm going to just go back and do that ratio one more time. If I actually copy all of this number instead of rounding it, I get exactly the same thing. So this would have rounded to 1.013, but without rounding, I can see that I really, really, really do get 1.013. It is important that these are the same. So I do want to have the same thing and to see that they are equal to each other. So even if it was rounded to 1.0, sorry, I can't talk. 1.0129 does round to 1.013. They should be the same. So what do you notice about the ratios of part C and D? They are equal. And what do these ratios represent? So it should also be clear that when we started with an increase of 0.013, this is similar to that, right? It's not the 0.013, it's 1.013. But they represent a 1.3% increase above 1 being 100%. So they represent a 1.3% increase. So the fact that we already knew that it was increasing by 1.3% is evident in the growth factors. All right. They're reminding us something that we already knew right here in this box. It says that linear functions have a constant average rate of change. Exponential functions have a constant percentage increase, and that's going to be our growth factor or our growth rate. They're related. Growth factor is related to growth rate. Okay, so we're going to talk more about that relationship on the next page, but let's see what's coming next here. Number 2, we want to make a table using the results from above. So I already know that my initial population is 141.4 thousand. After 1 year, it was 143.2 thousand. I got to round it. It won't fit in the box, the value I had up way up there. Then it was 145.1 thousand. I don't know those ones yet. I'm going to make the table from the equation because I prefer to do so. And I already have enough information to do it. I've already calculated that the ratios are the same. And remember that your ratios are your B value. So as we note down here, we already know the B value for this function is 1.013. This is our growth factor. That's the ratio from consecutive outputs for consecutive inputs. That's the ratio. In order to write the exponential function, I need the B value and I need the A value, but I can see the A value because it is my initial value. It is the value associated with my starting year. So this is our A value. So if I have those two pieces, A and B, I can write the function, and then I can use the function to fill in the rest of this. So P equals A, that's 141.4, that's what A is, times B, which is 1.013 to the T. Okay, so I'm going to go ahead and fill in the table from there. I think it's nicer than doing that repeated calculation again. So make it a function, P of T, 141.4 times 1.013 to the T. And I could make a table, or I can just do P of 3 and then P of 4 and so on. So P of 3 is, that's going to round up to 147.0. Then P of 4, 148.9 thousand. and P of 5, 150.8 thousand. So I made those in a different color just because I was using the function to compute those. The same process we used up here to compute them for parts A and B would have been fine. It's just, I think it takes more effort or more time to do that, and I think it's more efficient to use the equation. All right, so write the growth rate 1.3% as a decimal. So as a decimal, if I move my decimal place over twice, this would be 0.013%. We have already noted that as we did this computation for A and B. This is the decimal. Add 1, and this 1 represents 100%, the decimal. So 1 plus 0.013 equals 1.013. So we're going to note that if we have our growth rate, if we add 1 to it, what we come out with is our growth factor. So terminology on this, the growth rate is the percentage, and the growth factor is the base of our exponential function. Right, they're going to talk about this again on the next page, as I mentioned. All right, so up here at the top, we can see that the growth factor, B, is determined from the growth rate, R, by writing R in decimal form and adding 1. So B is equal to 1 plus R when R is written in decimal form. There's an example 2 right here, and then letter C wants us to solve the equation for the growth factor for R. So if I solve for R, I could subtract 1 from both sides. So B minus 1 would be equal to R. So we could do the reverse here. The growth rate R is determined from the growth factor B by subtracting from 1. So R equals B minus 1. And then writing the result in percent form because R is a percentage. So the two examples, let's take a look at them and then we'll talk some more. But if we had 8%, that's 0.08, that means that the growth factor, B, is 1.08. 8% is 0.08, so 1 plus 0.08, 1.08 is your growth factor, growth rate, growth factor. Or vice versa. If the growth factor is 1.054, if I subtract 1 from that and then convert it into a percentage, subtract 1 from that makes it 0.54, move the decimal place twice, then my growth rate for this situation is 5.4%. So the growth factor was 1.054, subtract 1, move the decimal place twice, I have the growth rate. There's the relationship between the growth factor and the growth rate. Okay, we'll talk some more about those. But first, we're continuing on with this population example. They want me to fill this chart in again, I think, for the function. So we kind of already did that in the previous page. I don't think we have a real need to fill it in again. You can see what the values would come out as because we've already done that. So I don't want to fill it in again. Okay, using the pattern helps you write the equation. How does your result compare with the equation obtained in example 2? They're just trying to show us, this is how we had referred to these equations when we did them in section 3.3. We would have looked at the pattern, we would have seen our equation, and this equation would have come out as P of t equals the initial value of 141.4 times 1.013 to the t. And again, that's the same equation that we came out with over here. It's just comparing the two processes for writing the equation. So we can write the equation either way, we get the same equation. So our answer should be that our equations are the same based on this process, which you would have done in section 3.3, as our new process from section 3.4. All right. Looking at the next page, number 5. in this example with this function, determine the growth factor. So the growth factor is b, and b equals 1.013. Determine the growth rate. The growth rate is r. R is computed by b minus 1%. So 1.013 minus 1, that's 0.013. So that means, move it the decimal place twice, 1.3%. So the growth factor B is related to the growth rate R. All right, part 6. Using the same function, determine the population in 2025. So I had originally been talking in years since 2016. So if we compute 2025 minus 2016, that gives us 9. That's where this t equals 9 statement comes from, because 2025 is 9 years past 2016. So we're going to compute p of 9. And I still already have my function in. So I'm just going to make it p of 9. And I get 158.83 thousand. All right, they want us to graph the function next. Now, it's already graphed because I have the function typed right here, but I can't see anything in this window. And I can't see anything because those numbers, 158.83 is large, and I can only see up things that are up to 5 tall, so they're going to help us rescale the window. If they didn't tell me how to rescale the window, I could always use the a value from the equation, 141, to give me a baseline, because that's where I'm going to cross the y-axis and then go up from there. But they have asked me to rescale this in a particular way, with 0 as the smallest x, 100 as the largest x, 0 as the smallest y, and 600 as the largest y. And now that I've got my function rescaled, I can see the graph. And the graph that I'm seeing here should match the calculator graph that they're showing right there as well. Okay, determine p of 0. What is the graphical and practical meaning of p of 0? Okay, so p of 0 is 141.4 times 1.013 to the 0th power. Anything to the 0th power is 1, so I get 141.4 times 1, which is 141.4. Now, they're asking me 2 questions here. One of them is the graphical meaning. So the graphical meaning is, this is the y-intercept. So if I scroll out a teeny bit, touch the y-axis, 141.4 is the y-intercept, or I could be more specific on this and say the y-intercept is 0, 141.4. And then the practical meaning, and that's where you tie in the situation. So we'll say in the initial year is 2016. So in 2016, the population was 141.4 thousand. Use our prediction to predict the population in 2031. Use our prediction to predict the population. That's got to mean equation or model or something to predict the population in 2031. Okay, so 2031 is how many years after 2016? We'll find that out first. So 15 is going to become our input value. And so what we're looking for here is P of 15. So P of 15 is going to come out as 171.6 thousand. Verify the prediction graphically. Okay, so graphically, Since this 15,000 is an input value, I can do an x equals 15 to see where this is going to hit my graph. And then I can see my prediction right here for the year 2031 is 15 years since 2016, and I can see that the output value is 171.629, just like I had seen on the algebraic or the function input method. So graphically, like we said, we have our function, we have our x equals 15, and we have our ordered pair right here at 15, 171.6. And that helps us verify the prediction of 171.6 thousand. So there's always more than one way to make a prediction. We made this prediction with a function. In function notation, we made this prediction here graphically. All right. Use your graph to estimate when Belleville's population will reach 175,000. So this is an output value, and remember that P is measured in thousands, so the output that I want to graph is just 175. Thousands are the units here, so I'm not going to put the zeros in when I graph this. Okay, so I'm going to turn off this x equals 15 because I'm done with that part of the prediction. Actually, I'll just get rid of it and replace it with a y equals 175. Now I got to turn back on. There we go. And it looks like it takes 16.5 years. Okay, so this gives us 16.5 years, or the ordered pair 16.5, comma 175. But 16.5 years is not going to be our final answer on this. It's 16.5 years since 2016, and so I'm not actually going to say that in my answer either. I want to actually add it on, but I wrote it down first so I know what to add on. So I'm going to take the 16.5 plus the starting year, which was 2016, and we'll say in 2032 and a half. So we'll round that to the nearest year and go ahead with 2033. So in 2033, because 0.5 forces the roundup on that, we'll say in 2033, we're going to round to the nearest year. The population, instead of in, I want to change this to by, just for clarity. By 2033, the population will have reached 175,000. Okay. All right, so that would be our answer there. And then evaluate P of 32 and describe what it means. So keeping my Desmos up here, plugging in 32. P of 32 is equal to 213.8. And when I describe what it means, I've got to talk about what the input and the output mean. So first of all, 2016 plus 32 for the input would mean that in or by 2048, the population reaches or will reach 213.8 thousand. Since I made a big deal about by, I'm just going to say why. Because I rounded this value up to 2033, it's happening in the year 2022, since it's 2032.5. It's still in the year 2032, but we don't refer to years as 2032.5. We say by the next year it will have happened. That's why I changed the word to by. No big deal. Just it doesn't really matter what word I use. My math I might use in instead, but by feels more legit to me. All right, almost done. Use the model to predict the population in 2019 and in 2039. Which are we more confident with and why? Okay, so first of all, 2019 is 3 years after the starting year, and 2039 is 23 years after the starting year. So we'll do our prediction for 2019 first. In 2019, we're going to compute P of 3. And P of 3 is 146.98. So I have to run it to 147.0 or 146.99. I already wrote 146, so I'm just going to keep 2 places on that because with 1 place it would be down to 147.0. And then I'll write 1,000 after it just because that's the units. And then 2039 is going to be P of 23. And that's 190.3 thousand. Which prediction are we more confident in and why? Well, remember that our initial year was 2019, and the further away we get from the data set and the initial values, the further we are, more error we're going to have. So this one is further from the data. And it's extrapolated. Actually, I could have just said it's extrapolated because that means it's further from the data, but that means that it's less reliable. So which one would be more confident in? We're more confident in 2019 because it is closer to the data. Now, in this particular situation, I didn't actually have data to start with. All I had was an initial value. I only had one data point. And from that one singular data point, we made a bunch of predictions. We predicted for 2017, we predicted for 2018. So I don't have a big, wide data set. So they're actually both really extrapolations, but the difference is a near extrapolation versus a far extrapolation. It's closer to the data, it's closer to the initial value in this case. So we're more confident in the 2019 prediction. Okay. Assuming the growth rate remains constant, how long will it take for the population to double? Okay, so let me turn off this one. First of all, you need to remember where it starts. It starts at 141.4. So if I want it to double, I want it to achieve an output value of twice that. So I'm going to take 141.4 times 2. And so I can just grab it like that, 141 times 2, or y equals 282.8. How long does it take us to reach that point? So we're going to double in 56.665 minus 0, or 53, I meant to say, or 53.7 years. Okay. So we did that a few times in the last section, so hopefully that makes sense. I'm doubling from the initial value, so I'm subtracting 0 from my x-coordinate here at 53.7 minus 0 is 53.7 years. Explain how I reached my conclusion in part A. So I graphed y equals 141.4 times 2, which was the 282.8. And the ordered pair right here was going to have that 53.7 minus 0 is 53.7 years. Hopefully that's a good enough explanation for how I did that. All right, we are finally done with the population of Bellevue, Washington, and now we're on to a wastewater treatment facility for our last example that spans this page and the next. We're working at a wastewater treatment facility. We are treating water contaminated with 18 micrograms of pollutant per liter, and our process is designed to remove 20% of the pollutants during each treatment. So it starts off with 18 micrograms, and I remove 20% of the pollutant each time. My goal is to reduce the pollutant to less than 3 micrograms per liter, and I probably want to figure out how many treatments are needed to do so. So what percent of the pollutant is present at the start of a treatment? What percent of the pollutant that is present at the start remains at the end of a single treatment? Okay, so 20% is removed. That means that if you take 100% minus 20%, means that 80% of the pollutants remain. They're asking me not how much is removed, but how much remains. So 80% of the pollutants are still going to remain after one treatment. The concentration of pollutants is 18 micrograms per liter. Determine the concentration of pollutants at the end of the first treatment. Okay, so 18 micrograms times 80% will give me, just make a new graph here, will give me 14.4 micrograms. Complete the following table, round to the nearest tenth. Okay, so we've already got the 14.4, like we said right here, after one treatment, 14.4 micrograms left. Okay, now that 14.4 micrograms is going to be treated again, multiplied by 80%. Then there are going to be 11.52 micrograms. They asked me to round to one place, the nearest tenth, so 11.5 micrograms. Then we're going to take our 11.5 micrograms times another 80% treatment. We're going to have 9.2 micrograms left. And again, our 9.2 micrograms times another 80%. We're going to have 7.4 micrograms left. And again, our 7.4 micrograms times 80%. We're going to have 5.9 micrograms left. Write the equation for the concentration as a function of the number of treatments. In order to write the equation, I need to know both the A value and the B value. I can see the A value as my initial condition because initially there are 18 micrograms. So the A value is going to be 18. The B value is the thing in which you would need to multiply to go from one value to the next value. We can get the B value by dividing consecutive outputs. So if I take, for example, the 14.4 divided by the 18, I get 0.8. And if I took the 11.5, or I believe it was 11.52, divided by the 14.4, I get 0.8. So this ratio is a multiplicative factor of 0.58. So 0.5, I can't talk. I don't know what 58 was coming from. I have no idea. But 0.8, I meant to say, 0.8. The 5 got stuck in my head from something. So I can see the multiplicative factor, my decay factor in this case, because these values are decreasing. The factor is 0.8. So that together builds our function C of n as 18 times 0.8 to the n. Now, is anyone surprised that their B value is 0.8 when we had an 80% remaining factor? That is not a surprise right there, hopefully. So, if you know the decay rate, R, then the decay factor, B, can be determined by 1 minus R. So I want to emphasize this because when they talked about the relationship between the growth rate and the growth factor, they had these like special boxes for it. I think they should have a special box here as well. So I'm going to write this off to the side that if you're talking about decay factor, your B is 1 minus your decay rate. Let's compare that to the other page. If you did your growth factor, your B is 1 plus your your growth rate, because you're growing. You're going above 100% by R. Now you're going down, you're decaying, so you're going below 100% by R. Okay, so that's one of our boxes. The other box, they said, let's take that equation that you had and let's solve it for R. So we can write a statement about how to find the growth rate from the growth factor. We're going to do the same thing for our decay rate. So if I solve this for R, I'm going to go ahead, because I don't want the R negative, I'm going to add R to both sides first. So B plus R equals 1, and then I'm going to subtract B. So R equals 1 minus B. And so my box for my decay rate, if I already knew the decay factor, my decay rate is going to be 1 minus B. Okay, so comparing that over here, the growth rate was B minus 1, because remember, B here is a number that is larger than 1. So if I subtract 1, I'm going to get a rate, and I'm going to convert it to a percent. It's going to be something that is positive, because B minus 1 will be positive. Over here, B, if it's decaying, B is a number that is smaller than 1. So I'll need to do 1 minus B to keep it positive, and we're going to convert it into a percentage. Decay rates are converted into percentages, just like growth rates are converted into percentages. So those should be in boxes. I wish that they were. So we have to make our own, because they boxed them out and made those special areas for us for the growth rate and growth factor. We need those for our decay rate and decay factor also. Okay, so over on to the next page. If the decay rate is 2.5%, what is the decay factor? So 2.5% is 0.025. And so my decay factor, B, it's 1 minus R, so it's 1 minus 0.025. It'll give us, let's find out, 0.95. 975. There we go, 0.975. Decay factors should be less than 1. If it's going to decay, your base, your factor needs to be below 1, as this is, 0.975. It's below 1 by exactly 2.5%. Now, this is the reverse. If the decay factor is 0.76, what is the decay rate? So we know that R, the decay rate, is going to be 1 minus B percent. So 1 minus 0.76 would give us, oops, I hit the wrong key, would give us 0.24, and then converting that into a percentage gives us a 24% decay rate. All right. Now, number 13, we have used the function C of n, which is the 18, this is the wastewater treatment, the 18 times 0.8 to the n, to predict the concentration of contaminants after 7 treatments. Okay, so we're going to do C of 7. And I don't think I have that function entered yet, so I'm going to go ahead and do that. So I can evaluate C of 7 here. Okay, so there are 3.8 micrograms of contaminant left. So they haven't hit their target yet. They were supposed to get less than 3 micrograms. They still have 3.8 after 7 treatments. Okay, sketch the concentration on the calculator. Use something, 11C, to set the window. What's 11C? Oh, the table. Well, I'll just set the window myself because I want to type the table in. I know that the highest output is going to be 18. I'm just going to shoot a little bit above 18. Let's say 20. I'm going to go to 0 because I know this can't go below 0. We can't go below 0 over here. And 10 treatments sounds good. So we'll start here. I can see that initially we started up at 18. Come on. And we're decaying. I set the boundaries on 0 on both X and Y so that I only saw things that were positive, and I just figured 10 wasn't too big, so we could see up to 10. Okay, so after 7 treatments, here-ish, we are still above 3. Does the graph look like I expected it would, is my next question. Well, what did you expect it to look like? So I know that an exponential function that is increasing would look something like this, and an exponential function that is decreasing is going to look something like this. So I should have expected this shape. I should have expected a decreasing exponential function. So yes, because it is a decreasing exponential function. So we saw those shapes in sections 3.1 and 3.2. We talked about the shapes of increasing exponential functions and decreasing exponential functions. So it looks like what I thought it was going to look like. Did it look like what you thought it was going to look like? I don't know. What's the vertical intercept? Well, we already know that it's at 0.18. I clicked on it a moment ago. And what is the practical meaning of this? That initially, so before any treatments, initially or before treatment, there were 18 micrograms of pollutant. Reset the window of your graph. Does the graph have a horizontal asymptote? Okay. Resetting the window to, they specifically ask me for -5 to 15 on X. And -10 to 50. Okay, I can zoom out a little bit too, because what I want to know is if this graph has that bottom border that it hits. I'm going to change the color, oops, over here, because it's black on black right now, so it's harder to see. I'm going to make it purple. I don't know if we can see the purple any better here. But this function is floating right above the x-axis. It's not hitting it. It's getting lower and lower, 0.7, 0.0 stuff, but it's not going to hit 0. So yes, of course, it has a horizontal asymptote. All exponential functions have one. It's just a matter of where it is. So yes, does the graph have a horizontal asymptote? Yes. And we can say that it's at y equals 0. What does this mean? So it means in the terms of the practical situation that we'll never be able to get rid of all of the pollutant, but we can just keep processing it out. It's always going to be teeny tiny or trace amounts. So the amount of pollutant can never reach 0 is what it means. Never reaches 0 because you're stuck just above 0, getting closer and closer and closer towards it, but it never reaches 0. So it gets close to 0, but it does not reach it. Okay, use a table or graph to determine the number of treatments necessary to bring the concentration below 3 micrograms. So we saw that after 7, we were not there yet. We're at 3.8. When do we actually reach 3? This is an output value. So we'll do a quick y equals 3, and then we'll come up with our solution. Okay, so 8.03, my ordered pair is going to be 8.03 comma 3. So 8 treatments is not quite enough. If I plug in 8 right here, you'll see that we're just barely above 3 micrograms. So you can't do 8.03 of a treatment, so you're going to have to do a 9 full treatments. You're going to have to round that up because it's not at 3 micrograms or 8 treatments. It's still just barely above it. So 9 treatments would be necessary.